In this video we're going to be looking at gas laws, and we're going to start off with a specific property of gases which is unique. Solids and liquids do not have this property, so it's only true for gases, and that's compressibility. So compressibility is the measure of how much your volume decreases under pressure. So if we were to take these gas particles and squeeze them into a smaller space, we could do that. That is going to increase their pressure when we decrease the volume that they're in. Now the reason that gases can compress but solids and liquids cannot has to do with the space between the particles. If you notice a solid, there's very little to no space between the different particles. They're held very close together. Liquids, there's a little bit more motion. That's why liquids can take the shape of their container, but their volume is fixed. So they, a gallon of milk's a gallon of milk. You can't take a gallon of milk and try and squeeze the whole gallon into a small drinking glass. The volume isn't going to compress. But you can in gases. We can force the gas particles, because of all this empty space between them, we can force the particles closer together and then of course force them into the smaller container. When you do that, it increases the pressure. Now there are three things that affect gas pressure that we're going to get to starting on the next slide, but just some general things about gases before we get into that. One, particles move in a straight line. So there's no wiggly, wobbly, in and out, weaving around things. They move in a straight path. When they hit the wall of a container, they can bounce and go into a different direction. Think of if you've ever played pool. When two particles hit each other, they can bounce in different directions, but they stay in a straight line until something collides with them, or they collide with the wall. There's also no significant attraction between gas particles. So if these two gas particles were really attracted to each other, then they would want to be close together. But since they don't have attraction between them, one can go in one direction, one can go in the other, and they're not attracted or wanting to stay close together. If you have ever listened to the weather, you may have heard them talk about a barometer, or what the atmospheric pressure is. But pressure is measured with a barometer. That's the piece of equipment you would use if you wanted to know what the atmospheric pressure is. Now, getting into the factors that can change our gas pressure: the amount of gas that you have, whether you increase or decrease the number of gas particles, the volume, and then the temperature of the gas will also increase or decrease the pressure. So let's look at each one individually. So the amount of gas that you have. If you add gas, you are going to increase the pressure. So adding, increasing, we call this a direct relationship, because when one goes up, the other goes up, or when one goes down, the other goes down. They're going in the same direction. The more particles that you have, the more the gas particles will be colliding with each other, and that will result in higher pressure. So in all cases, collisions are incredibly important. The collisions are where the pressure comes from. So the more collisions, the more pressure, and the fewer collisions, then the lower the pressure is. If you put air in your tires of your car, you're adding more gas particles, so they're going to collide more often, and therefore the pressure is going to show up as being higher. Now volume is the second of the three. And we do need to think about a closed container, because we said that gases will take the shape and volume of the container. If you have an open container, those gas particles aren't in there anymore. They are out filling up the rest of the area that you give them. So we have to have a closed container, but if we reduce the volume, then the pressure goes up. So reducing, going up, notice that when one goes up, the other's coming down. So we call this an inverse relationship. But the reason that happens is that there's less space. Now, if you decrease the volume, there's less space for the gas particles. They're going to collide more often. Pressure goes up. Reverse is also true. If you give them a larger container, so the volume goes up, now they have fewer collisions, and so the pressure goes down. The third one we said was temperature. And again, for a closed container, if you increase the temperature, for instance, you take a pop bottle maybe, and fill it full of air or something, and put it into a fire, a bottle that isn't going to melt. The particles in that bottle are going to be moving much quicker And the reason that they're moving faster is because of their kinetic energy. Kinetic energy is the energy that you have from motion. So whenever anything's moving, it has kinetic energy. When the temperature goes up, it causes the kinetic energy to increase, and so they're hitting the container, they're hitting other gas particles more often, and you see an increase in the pressure. So increase in temperature, increase in pressure. Here's another direct relationship. Also, if you were to take a container and put it in the freezer, for instance, you would maybe see you would see the pressure come down because you have less kinetic energy, the particles are moving slower, there's less collisions, so less pressure. First gas law that we're going to look at is Boyle's law. And in Boyle's law, you need to have some things that are constant or not changing. So the temperature is constant, and also the number of particles. The number of gas particles isn't changing at all. The things that we are looking at is the volume and the pressure. So we can see in this line graph that as your pressure is getting higher, your volume is getting lower. High pressure, low volume. If we have a low pressure, then our volume is high. So this is an inverse. An inverse relationship is always going to show up as a curve because of the one increasing, one decreasing. So if we were to double our pressure, we would be cutting our volume in half. So if we double one, we're cutting the other in half. Think of it like in math, an inverse. So if you have 2, you're doubling something. The inverse of 2 is 1/2. So that would be the relationship that we have here with volume and with pressure. Now, in order to mathematically show that, we are going to have pressure and volume being multiplied together. So if we know what our initial pressure and initial volume of a certain gas would be, we would need to know one of these other two factors. We either need to know what the pressure is or we need to know what the volume is so that we can calculate the other one. So you have to know 3 of the 4 unknowns so that we can calculate what the unknown is. And so we're going to look at practice problem 1. In this case, we have a balloon that has 30.0 liters of helium gas, and we know that the pressure is 103 kilopascals. So liters is a measure of volume, kilopascals is a measure of pressure. Another pressure unit you may see would also be atmospheres, but kilopascals is really common. So we know that the volume, 30 liters, and 103 kilopascals for the pressure. And then the volume of the helium balloon, we want to know what the volume of the helium balloon is when the pressure reduces to 25.0. So we know that our pressure starting at 103, it's coming down to 25. So if we were to put all of these items into our data, into a little table here, so that we can put them into our equation, we know that the original pressure is 103 kilopascals at a volume of 30.0 liters. And now we know that the balloon is rising to an altitude of 25 is our new pressure. And the question is, what is the volume? So the volume is our unknown, it is our question mark. And not just volume, but volume 2. We don't know what that new volume would be. So our equation, pressure 1 times volume 1 is going to equal pressure 2 times volume 2. And we are going to plug in all of our numbers and units. And we need to make sure that they cancel. That's why units are important. It tells us if we did something wrong or right. So I'm just plugging in all of the information where it fits into the problem. And now I need to solve it. So this is where your algebra skills need to kick in here. We want to get volume 2 by itself, and so to do that we need to divide by the 25 kilopascals. And what we do to one side in math, we need to do to the other side so that it stays balanced or equal. So kilopascals and 25 are on the top and the bottom, so they will cancel out. And then we're left with just the volume 2. And over here, your kilopascals will cancel, and you're left with just liters. This is another way where having those units is beneficial. It tells you what your unit should be at the end. Now multiply 103 times 30. and then divide that by 25.0. And we have 3 significant digits in each one of these numbers, and so our answer needs to only have 3 significant digits, and that should be 124. Alright, let's start the next one, and then I'm going to have you finish calculating it. But we at least want to get it set up here. So we need to know our first pressure, our first volume, second pressure, second volume. And again, one of those is going to be unknown. So let's read through this and pick out our numbers and put them where they belong. A gas with a volume of 4.00 liters at a pressure of 205 kilopascals is allowed to expand to a volume of 12.0 liters. So originally 4.00 liters has a pressure of 205 kilopascals. So our original pressure, 205, and our original volume is 4.00 liters. Now it says that the balloon is allowed to expand. The volume is now 12.0 liters is our new volume. And the question is, what is the pressure in the container? And the temperature remains constant. So that's just telling us the temperature is not a factor that we need to include in the equation because it's not changing. So pressure 2 is what we're looking for. We're still using our same equation, Boyle's law, pressure and volume, and we're plugging in all of the numbers that we're given except for our unknown. That's what we're solving for. So we don't know what our second pressure is, but we know the second volume, 12.0 liters. So now your algebra skills still kicking in there. Got to get P2 by itself, so we're going to divide by the 12.0 liters on both sides. Now liters cancels and we are left with kilopascals, which makes sense since we're asked for a pressure, and 205 times 4, and then you're dividing that by 12, and all of these have 3 significant digits, so 68.3 should be the answer that you end up calculating.